Me? Yeah, good. Yeah, so I just got internet here, right? So I can just show you the very useful Agda wiki. And I've put up the page with editing commands. Here are some of the most important commands. Some of them I told you last time, Control-C, Control-L for load. I told you Control-C, Control-Space for give, the complete expression. Control-C, Control-R for refine. And normalize, Control-C, Control-N. I will now go on and show you, K-split. This is when we get into inductive types. So I also wrote the URL. I hope it's right. Maybe I can show it to you. So here is my web page, and there are, actually quite a few papers that I have written in the past are somewhat, related to, well, a lot of them are related to type theorem, I'm afraid. And some of them are perhaps could be of interest to those of you who are, well, interested in research in this area. There are also some introductions.
Peter, do you see the power node?
Ooh, why isn't it something about? There it is. Thanks. Yeah, you saved me. Yeah. So there are some of those papers are. I may put some links on the material for the 2015. So actually, did I write my own URL correctly? No, I didn't. Well, anyway, you will find it. So I told you about the article for Stanford Encyclopedia. I told you about 3 of the key papers by Per Martin Löv. I have put up a file here, the directory that I started showing you last time. I didn't get to show you the whole of this, but I did something a little bit similar to what's in the file combinators.agda. Since I am a little bit behind schedule, I was really meaning to show some other things that you can do in the pure logical framework, but I think I will postpone that a bit just to make sure that you see the basic stuff so that you can do some of the basic exercises requiring inductive types. If you want to get started with Agda, it's better that you see how to define natural numbers and Booleans and predicate logic and stuff like that. Then you can do the first exercises. So you can also let's see. So you can also look at the Agda exercises. So some in the beginning very easy, but they require you to know about Booleans and natural numbers and predicate logic and so on. So I think I will show that first, and then maybe at the end of the hour or next time I will show you more about what you can do with a pure logical framework without introducing any inductive types. So have you got any questions on that?
Could you draw on your web page just a little bit longer?
Sorry, if
the web page, your web page address you had on.
Oh yeah, yes. Yeah, so it's like that. Yeah, so you see that one is where, and I'll put more stuff here as I go along.
Google for Peter D. OPLSS, you find it.
Yeah, exactly.
So it's a first setting of to show the whole thing instead of typing it.
Okay, so let me now go into, to use Martin Löw's terminology. Before I talked about the theory of types, the pure logical framework, the pure lambda calculus with dependent types and one universe, where the universe is called set for, sets, as Martin Löw decided to call them. Why did he call them set? Well, his idea was that set in mathematics corresponds to data type in programming. He, for the theory of types, he thinks of types as something general, and he would call it logical type. Type as it was already developed in logic by people like Church, for example, beginning with Russell Ramsey, and then Church, who designed the state-of-the-art classical type theory, which I will show you a little bit of later. So that's his terminology. I mean, the term set is kind of captured by several different people with several different meanings. It means something different in Koch. It means something different in homotopy type theory. So one has to be a little bit aware of that. But Martin Löw, he hogged this word for data type. And the data type, according to his philosophy, is something like inductively generated type. And the way it works in the logical framework-based theory is that you add constants to this theory. So for example, if you want to introduce the type of natural numbers, which is, as Adam said, the simplest one, which deserves the name, then you add a new constant for the type, of n, big N. I actually use the word, I use not, but I will use different identifiers for the Agda code. But I add a 0, n is a set, so it's also a type, and then I add successor. So now I have somehow defined the natural numbers. This we call formation rule. I'm probably repeating some stuff that Bob already told you, and maybe Frank. And those two are called introduction rules. I mean, they are typing rules for constructors. I mean, what happens is that terminology from programming gets merged with terminology coming from logic. And sometimes one uses the one thing and sometimes one uses the other. And sometimes, there are synonyms for the same thing. And then, we have the elimination rule, which Adam had it in Koch notation in his picture. So I will maybe not write it out here since it will come on the Agda code, but it will be some kind of long type which expresses typing of primitive recursion combinator, or equivalently as proof by mathematical proof object by mathematical induction. And I will show you on the screen what it looks like. And then, one will add equations for rec, on 0 and on successor. Again, I won't write it out here since it will come on the screen later. And those, this was called elimination rule. And in Martin Löw's terminology, these are called equality rules, or sometimes, computation rules. Yeah. So you do this for each inductively defined constant that you add to your logical framework. So let's show how this. Yeah. Any question? So let's show you what this looks like in Agda. So, yeah, let me just, you remember here, the whole. Yeah, etc. We'll just kill. Okay, let's show you the natural numbers in Agda. So, of course, it will be a little bit similar to stuff that Adam had. Of course, I feel a little bit intimidated by Adam and his LTAC wizardry. Unfortunately, there is no LTAC wizardry in Agda. We once employed a research assistant to do something like that, but it actually didn't really get off the ground, and people haven't really prioritized that, as I said. What we have in Agda is something that you're not allowed to use until you have got up to speed with Agda. You have Control C, Control A, which is the automatic tactic, which, yeah, in some situations it's quite clever, but it doesn't go such a very long way. There is, of course, a debate, as to whether the value of automatic proof, of course, Adam was, propagating the value of not understanding. And it's quite interesting that for people like Martin Löw and Thierry Cocon, and we had the same discussion with Voevodsky, who was visiting Gothenburg lately, they're all very negative to automation, as long as it goes beyond automation of very trivial facts. It's some kind of philosophy. Yeah, anyway, so I have this file, NUT, which is a module, and so now I have a different directory of inductive types. So it's in there, and you now see, is it the right size, by the way? Is it okay? Yeah. So now you see how you write the inductive definition of the natural numbers. As Adam said, well, also in Agda they are defined from first principles. They are not God-given, as in normal programming languages. They are inductively generated by zero and successor. So you see here, right, that actually we don't have a pointer. Yeah, anyway, I don't think it matters. You see here that this is syntax which is supposed to give you these three typings. You see that we use the keyword data, the same keyword that one uses in Haskell. And then we say, now we declare the type NUT. And we have to give the type. In Haskell, you don't need, you just declare a recursive type. But now we have many kinds of inductive definitions, and I will go on, and explain the more sophisticated kind of, inductive families, inductive recursive types, and so on later on. So therefore, it's necessary to give the type of the thing that you are inductively generating. And then you write the constructors below, and you have to do some indentation there in order to make the system understand that these are constructors. And then, you can introduce abbreviations of, numbers like 1 and 2, and so on. And then I will show you the elimination rule in a while, but I will first just show how you write definition by pattern matching. So let's comment out these equations here. Let's just do the very simple thing of defining the predecessor function. So what you do here now is that you write, you want to define a unary function. You write it in functional programming style. Predecessor of n is something which you don't know that yet. And then, so we type check, so we make sure that we didn't make a mistake yet. So now we have to see what is the right-hand side here. And in Agda, you can now expand this pattern here. You can expand n to the different cases. And then what you do is that you enter the variable which you want to expand in the hole, and then you do Control C, and then you get the two patterns. Yeah, and then you just have to fill in the right-hand sides here. Maybe we can do it automatically. Maybe they know. Maybe the auto knows. Should we see? It did. Maybe it knows here too.
What are you typing there?
Control C, Control A. So auto knew in advance that I was going to write the predecessor function. It probably says that it's the simplest possible unary function that you can define by pattern matching, because I mean auto somehow searches around for different possibilities, and this is what it tried first. But of course you could have filled it in with Control C, Control space, and Control C, Control R as well. Okay, so that's how you define, how you do pattern matching. Yeah, just as Adam showed, you see, I'm showing some of the same things as Adam based his proofs on. So for example, we define plus in this way that one knows from logic by, primitive recursion. So here I have chosen to do it in the second argument. And this is of course something, if you are not yet used to programming with dependent types, that you should be very careful when you define something, whether you do it in the left or the right argument, if it interacts with other definitions, because otherwise it may not type check when you think it does. I mean, the type checker will use these equations during the process of type checking. They will normalize types with terms in them according to these equations, and you get different results depending on how you wrote your definition. So be careful. Right. Yeah, here is another one. There is just definition of subtraction. It's not. Yeah.
Could you just show us an example of like a different way of writing that might cause us trouble? Like this is...
Well, so what causes trouble is, for example, when we are not somehow yet there, but if you define, the type of vectors over a certain length, and you want to define the append function, and you want the typing to say that when you append two lists, then the result has the sum of the lengths of the lists, then the typing of that function will depend on how the addition function is defined. So that's an example. If you do it the wrong way, you will get into trouble. So we will see that example later. Yeah, so maybe the point of this subtraction example is just that you can pattern match into arguments, Well, why don't I do it? Yeah, so you see here, so m minus n equals so we do, for example, pattern matching in the first argument, and then you see 0, well, it's minus, it's cutoff subtraction, so 0 minus n is not allowed to be less than 0, so it has to be 0 here, and then the other case you pattern match on the other variable, and then you refine here, and here you have the recursive case, like that. Yeah, by the way, Andrea told me something that I didn't know that, but that makes life simpler. You can write lambda as backslash, what was it? LG.
Capital G and F.
Capital
Capital G and F.
like that.
Yeah.
Greek L. And 2, what was it? Backslash R. Yeah. So that saves some keystrokes. Right. So here you have primitive recursive definitions, yes. And then, so Agda has a feature for using decimal notation. So you can use built-in natural numbers, which gives access to ordinary decimal notation. So if you want to define 10 as 10, Agda will understand that after having read that instruction. And yeah. And similarly, you can make sure that the execution of plus uses the built-in machine addition in this way, and similarly for multiplication. Yeah, you define multiplication in this way, of course. And there are a number of other built-in types: integers, floats, strings, characters. And actually, yeah, so I was just going to show you some computation. Here is how you compute, just writing it line reduction by reduction. And if you do Control-C, Control-N, it will execute that. Yeah, a few more. You can declare an infix operator to be left associative. So for example, here plus and times are left associative, and you can give precedences so that you can omit some parentheses. So with this, x plus y plus z without parentheses will be, it associates to the left and automatically inserts the parentheses in the right way. And you can see this by writing this function. Yeah, so here is the primitive recursion combinator in the, it's not dependently typed. This is just simply typed, but polymorphic. The only use of type dependency is that we make it depend, it's polymorphic in big X, so it depends on big X, which can be an arbitrary small type. And it's a ternary function which takes a base case and a step case, which takes a natural number in the previous result to the result for the successor. And the equations are the following, which should be familiar to you. So the system, which is just simply typed lambda calculus, this is also good to know somehow general knowledge. So simply typed lambda calculus plus natural numbers with 0 successor and, well, I call it NatRec, or yeah, NatRec, primitive recursion combinator, is, and of course there are typing rules, is called Gödel system T. And this is a very important system in logic, I would say. Gödel 1950, I remember 57 or something, 57 or 58. Invented already in the 40s. So this is important because it's one of the mothers of Martin-Löw type theory. It's some kind of mini Martin-Löw type theory which just has simply typed lambda calculus and rules for natural numbers, but it's still a very theoretically very powerful programming language in which you can program not only all primitive recursive functions, but also primitive recursive functions of higher type, like the Ackermann function. So theoretically, it's probably more than what you ever would want, but of course practically it's inconvenient. It requires that you encode everything in terms of natural numbers. But it's good to know about, and it's a typical example of a language where all programs terminate in a certain sense, in the same sense as in Martin-Löf type theory. And of course, Gödel system T is a kind of subset of Martin-Löf type theory, and the way you encode it is by using the encoding NATREC like that. I mean, note that in Gödel system T we have no dependent types, so instead we have to have one combinator for each big X, so there is an infinite family of combinators. But here, you know, we have just one dependently typed combinator. Right. Yes, so this is natural numbers. Is there anything more? Yeah. Oh yes, of course, from a theoretical point of view, it's sort of important to know when you can reduce a function defined by pattern matching to a function expressed completely in terms of NATREC. So the way you write plus in terms of NATREC is in this way. You know, the base, say that you do induction on n, base case is m, and the step case is to map the previous result to the successor of the previous result. Yeah, so of course Agda requires all programs to terminate. So in particular, it does not allow this definition. And you see it says termination checking failed, and it recognizes where the problem is. And you know, this is the color which should make you unhappy. The other colors make you happy, but this amber color makes you very unhappy. You have created inadvertently, hopefully, a loop somewhere. So I mean, I think this was also hinted at by Adam, you know, that Koch and Agda don't exactly implement primitive recursion, but it implements something which is a little bit less primitive than primitive recursion, but still ensures termination. And this is a topic of current research to generalize the termination checker so that it accepts more programs. There is, for example, an approach using so-called sized types, which tries to recognize more and more programs as terminating.
So is NATREC something you need to write yourself, or is it something that systems provide for?
No, in Agda doesn't have you have to write yourself, but of course one could imagine a beefed up version of Agda which automatically generated the elimination rule for you, but it doesn't.
So for every inductive type you write, you have to write only one?
If you want to program in that way, yes, you have to do that, but of course most people, it's only people on the far theoretical side who want to program like that, but it may sometimes be of interest. But otherwise what you do, is that you write these functions by pattern matching and make sure, that the right-hand side has the right shape so that you know that it's terminating.
How do you turn off the termination checker?
Yeah, you're right. I will show you a little bit, but I don't. Let's see if I have. You write something at the top. No termination check. I'm not sure I remember the exact sequence. Do you remember, Andrea?
Yeah, so it's in the track map.
Yes.
The options dash no termination check. Okay. On this tab.
Yeah, so there are various checks so that you can turn off the termination check. You can turn off, I will come to that later, the positivity check for data types, which forbids certain data types that you can write in Haskell. And there is also coverage check. Can you turn that off too?
Yeah.
Yeah. So coverage check that if you write your pattern matching equations by hand, then Agda checks them that they exhaust all the patterns. Right, so yes, actually. Well, so, how it's possible that we write built-in, yes, that we write 10? Yeah, so it's that, the Agda system matches the definition of natural numbers. It knows that nat is, it looks at nat, and it somehow knows just by convention that 0 is 0, as written as a decimal number, and that successor is the successor function. And when you have 10, that it builds it by 10 successors applied to the 0. So of course this is, there is a reason for why one wants to define things from scratch, which has to do with the fact that it's a logic, where you prove things by induction, which depends on the things being built up by 0 and successor. So in this way you get somehow the best of both worlds. Yeah, so I think actually I put this as an exercise, so maybe I'll delete it. Ackermann function. Yes, this is not so much. Yeah, so this is just to show you that you can use let notation and where notation in your programs as well. So like in an ordinary functional language. Okay, Booleans.
One more question, please.
Yeah.
If I write a function with a condition, for example, if x less than so if I don't cover all the possible cases, does it check that?
Yes, Agda checks that. Of course, if you use Control C, you automatically get a full covering set of patterns. But if you write the patterns by hand, by yourself, you may miss some pattern, and then Agda recognizes that you do that. Right. So Booleans. Well, yeah. So here comes actually a new feature. I think Adam had something similar in Coq. Oh, there we are.
You need to comment out.
Ah, yeah, yes. Otherwise it. So Booleans. Sorry, I know it's a little bit slow going at the moment, but it will get faster in due course. It's yeah. I don't know. This is probably not very much to say. We just need Booleans, of course. There are some, just a bit of use of Unicode. Yeah, I think I've shown all of this. Of course, the elimination constants for Boolean is if then else, and here is the simply typed version, which is just polymorphic in the C here. Yeah, so something which is a little bit interesting is, of course, that a very important function to write is the equality test for natural numbers, which you can write by pattern matching in 2 arguments. So this is the kind of thing which is accepted by Agda, but which is a little bit non-trivial to write if you work simply in Gödel system T, because you have to write it by the primitive recursion combinator by somehow a repeated use of the natrec combinator. So yeah, so I think it's done here. I won't go into the detail there. Yes, so now I am actually referring to a file called propositional logic. So maybe I should show that first, but remind me that I should go back to this after that. Yeah, so the next step. So we have seen 2 examples of inductive types, one natural numbers and the other Booleans. From the point of view of type theory, the logical constants are also inductively generated. They are inductively generated from their introduction rules, the constructors of proofs. So yeah, I'm sure that this is stuff that Frank and Bob has shown you already. So for example, OR is an inductively defined type with 2 constructors, proof of the left disjunct and proof of the right disjunct. So here you see some other new notation. We could put, I mean, what we get in this case here is or. Yeah, so this I should also say, you know, that if you want to use the or symbol standing alone, you have to write it with the underscores. This is the way you write this, you know, infix operator as a symbol standing alone. And of course it will give you something which binary functions on sets, or, you know, sets standing for propositions. So why do we write them to the left of the colon in this case? Why does it say phi psi colon set and then colon set? And why don't we write it like that? Anyone has any theory about that? So this is what, you know, the system will read this and we'll see that, yes, we have a new constant for type checking. It has this type. So why don't we just write it like that in after the data? John?
They're used uniformly in the output constructor.
Exactly. So this is the disciplined way of doing it. So we call them parameters. Phi psi in phi or psi are parameters. They are used uniformly in the definition. And in those schema for inductive types, it's essential whether something is a parameter or whether something is an index in an inductive family, in an indexed inductive definition. And you can somehow, you know, make that clear by writing it to the left of, writing the parameters to the left of the colon. So Agda will not check adherence to a specific schema, like, you know, either, well, something I developed or something similar that was developed for the calculus of inductive constructions. For Agda, this is simply a way of saying that phi and psi should be implicit parameters in the constructors. So you don't need to adhere to this principle that parameters are arguments of a type constructor which are used uniformly in the definition. But it's good discipline to do so unless you have a specific reason otherwise. So the elimination rule, as we know it from logic, you know, for or says that in order to prove something from, you know, prove a property, is it an x or a chi? I don't know, chi, from phi or psi, we need to prove it for phi, and we need to prove it for that it follows from psi. And in this proof normalization way of analyzing logic, we say that a proof, yeah, so I'm sure, you know, I haven't looked in detail at Frank's lectures, but he has shown you that, right, proof normalization. And this is just how you express those proof normalization steps in Agda. I mean, you saw these figures of proof trees being simplified, right? And this is exactly how you express that in terms of Agda's proof objects. And they turn into, you know, definitions of the function, you know, the elimination constants becomes a function which builds proofs, and it can be simplified if you have specific proofs of introduction form in its, so this is called the main argument, right? Main major argument. So this is how you define or with its introduction and elimination rules. You go on, you know, with and, there is just one constructor building a proof of phi and psi from proof of phi and a proof of psi. Here you have two elimination constants, one which from phi and psi returns phi, and one from phi or psi returns psi. And similarly, there are proof normalization equations coming with those elimination rules. And again, phi and psi are parameters. So it's quite nice when I looked a little bit at Frank's and Bob's lectures, and in a way an exercise would be put it into Agda or Koch, because especially some of the calculations that Bob seems to have done on the board could actually be done in the system, right? Yeah, this is probably all extremely well known to you. This is the way you look at implication as being inductively generated according to Martin Löw's philosophy, that all sets are the same as propositions. They are all inductively generated. The implication is generated by, the implication introduction rule, which says that if you can prove psi from phi, then you can prove phi implies psi. And the elimination rule, it corresponds, it's the modus ponens corresponds to application, and it has something, which is the beta reduction rule. So of course there is a discussion, whether actually it's not better to think of implication as being co-inductively generated. It will sort of be defined by its elimination rule. So we get into the co-inductive aspects of Agda, which is not somehow in the original Martin Löw approach, but it's something which people in Gothenburg are working on. I will show you records later on, and records can be recursive, so you can have co-inductive types and so on. So this is a topic of current research to somehow extend Agda to that sort of thing. But something which is also you need to know about Agda is that you have empty pattern matching. So falsity is defined as the empty type, the type or the empty set, the set with no introduction rule. And then you have falsity or absurdity elimination, saying that from absurdity you can prove anything. And you prove this by, pattern matching, by case analysis. There is no case. And in previous Gothenburg systems, what happened when you did case expansion of say that we define this, like we say, how do we prove phi from bottom? Well, we do case analysis on the proof of bottom, falsity, absurdity. And when I hit Control C, this equation would simply disappear. But Agda, being a little bit more of a conservative, says we shouldn't just let it disappear. We should have some kind of notation for saying that there is no case. And this is Agda's notation. And when you have repeated pattern matching, you can see that the place where there is no case can be embedded in a more complex expression. So this is important to know about, because this, of course, happens, when you do more complex things, that cases disappear because they cannot appear. They fail the matching.
So as far as doing these kind of proofs in Agda goes, do you need this bottom elimination rule, or does it have a place, or could you have gotten rid of it?
Well, I mean, certainly when you do proofs, you quite often come into cases where you prove something because something is empty. There is no case to analyze. Yeah, so you have to have it in some form, right? Yeah, so the trivially true type, it's the type with only one constructor. It's the singleton type, and there is no elimination rule. And of course, negation is defined as in intuitionistic logic as implication into absurdity. Right. So now I should just go back to define this important function. I think Bob said in his lectures, that it's very, very important in intuitionistic logic to distinguish between truth values and propositions, between Booleans and propositions. I mean, classically, they are the same, but here they are something different. So bool is just a type, well, a set with two constructors, whereas, proposition in general is a type. But it happens quite often that you want to convert from a Boolean to a set, to a proposition. And here is a function, I call it so after, this is a pun by Conor McBride, one of the main proponents of dependently typed functional programming. So I think it's because, he calls, for example, he calls the constructor for true top, he calls it little o, so you get oh so true. So true is the one element type, so false is the empty type. Yeah, so as he also says, a Boolean is a bit uninformative. This is, of course, independently typed functional programming. One often doesn't want just to return a Boolean, but some kind of disjunction with information about why something is true or false, right? When you do this sort of style of dependently typed functional programming, explored in particular by Conor McBride and Ulf Norell and Nils Anders Danielsson, are also people who are really sort of making this into an art, putting a lot of information into your types. Then you typically don't use a Boolean, but a more complex types, saying why something is true or something is false. Yeah, so I don't know. There are some more functions. I think I should not spend too much time on them. Well, okay, so let's, you see, sometimes you will somehow need little lemmas like this when you reason about Booleans. If we have proved, from a proof that the Boolean is true, we get a proof that the Boolean B or C is also true, and this is a function that you need to define by pattern matching like that. Yeah, and here you see a case where you see an example where we have an empty case appearing in the third branch. So why is that?
Could you show us the definition of or again?
So yeah, so it's defined by pattern matching in both arguments. So they're all.
Somehow it's a little more complicated than you would need with the idiomatic construct, where you have one pattern match on one argument, and only one of those two bodies would need a further pattern match. But if you see it true,
right.
you pattern match again, and this proof would then get shorter.
Yeah, exactly. So that's of course true. That I'm not sure why did I write it like that, because that's of course unnecessary. I don't remember.
So you could put an underscore in place of the second occurrence of the word true and delete the third case, and maybe that would be fine.
Yes, let's see. So you say like that. Yeah, it doesn't do it automatically. So, in this case, it kills that case, because it's the case of so B when B is false, right? So there is no such thing. So B is empty, so there is no such thing. Right. Yeah, so here is a proof of reflexivity of equality of natural numbers, which Yeah, so in order to understand this, we have to go back to the definition of equality of natural numbers, and you see that in the case of 0, it will return a one-element type top, and then you have the top introduction. In the case of successor of n, success equal of successor of n, successor of n, then it simplifies to equality of n and n, and hence the reflexivity of equality will also reduce to the case for n. Sorry, once again.
Could you please foil the proof, for example, if comments may reflect not zero light, just to see what Idris said?
So what are you suggesting me to do? To
Introduce a problem purposely.
Comment the line of any of line of the proof.
yes, like that.
Yeah. No, we're no only one. Yeah, just
Oh yes, okay, yes, that's a good idea. So you see it says incomplete pattern matching. Yeah, good. Thank you. Okay. Propositional logic. Let's go to predicate logic. It's also no great shakes, but let's see it anyway. Yeah, so here we see a new feature of maybe enlarge it a little bit. Please shout at me if it's too small. Yeah, here I just wanted to show you how to define predicate logic. And we have to have a domain of quantification. So let's just introduce a set, call it D for domain. And now we postulate it. So this is a new keyword. You can postulate a constant. I mean, logically, it's just like putting a new assumption, a new variable, which is somehow global, within the module you're working. And then you can, of course, use it later on. So now you see that you can have the existential introduction rule written like this. I mean, if you, for example, go to the Wikipedia article on, I don't know, predicate logic or something, and you see them explain exactly the rules for quantifiers and so on, and all this business about the variable capture in rules and so on, and then you of course see the power of this logical framework approach, where you once and for all take care of things like variable binding, substitution, and so on, so that the rule becomes so clean and simple as here. So it says, that if you can prove a property phi x for some x, then you can prove exist x phi x, and of course it comes here in variable free notation. So yeah, so maybe I should say that too. So the existential quantifier has a predicate phi, a unary predicate on the domain D, and then it returns a proposition. So exists has one argument, since D is not it's just postulated. And the elimination rule, to how to prove psi from exists x phi x, is that you prove psi for phi of x for an arbitrary x. And then, there is the proof simplification rule, which looks like here, that if you eliminate on an introduction, then you can simplify it. So we are getting to the definition of the universal quantifier. So this is the way, I talked last hour about the fact that Martin Löw does not accept one of the rules for forming dependent function space. So instead, he wants to have it like this, right? That when you introduce pi, it's similar as the universal quantifier, then you add, it's a new inductively defined data type, which is just like the function space, but it's a dependent function space. So if you can prove that for any x in D phi of x, then you can prove for all x phi of x. And that's how he encodes the rule, that we eliminated. So I can't say that I have, John's question whether the systems are actually equivalent. I haven't checked, but it sounds plausible. We have to sort of show that there is a one-to-one correspondence between the two. The reason why Martin Löw wants to have it like that is because he wants every data type, every set, every to be inductively generated. So this is a sort of formal reason which makes it like that. But the designers of Agda has not respected that.
Question: if we'd like more traditional notation for the quantifiers,
Yes.
then like if I wanted a dot instead of an arrow.
Yeah. So there is a feature called syntax which
Okay.
can return some quantifier-like notation for the quantifiers, which is more traditional. I think I actually have it, not in this file, but in a later file. I will come back. I think I wrote it in the file where I have the full Martin Löw type theory, so I can show you there. It's a little bit, complex to exactly define, but it's possible. Yeah. Yeah, so the reason why I had a for all prime is that Agda, yet another notational variant for Agda, is to use the universal quantifier sign for the dependent function space. And it's of course particularly intuitive when you want to use this function space for universal quantification. And then you don't need to put in the type of the argument. So this is also, I think, they took from Koch. Okay, now, yeah?
So, I didn't understand the prime.
Yeah, so, okay, so.
It means something special?
No, it's just to avoid clash of, for all is reserved for this particular shorthand for dependent function space. That's the only reason, Because of course in practice, people who work with Agda never uses this Martin Löw style definition of dependent function space for set. Right, so next thing I wanted to show you is also if you have predicate logic with identity, then Bob has spoken a lot about identity in type theory, so it should also be very familiar to you that identity is defined as, well, the least reflexive relation, if one wishes. The relation which is inductively generated by the proof of reflexivity, or you can call it, using logical terminology, equals introduction. And then the elimination rule is that you go from a proof of x equals y and a proof of phi of y for some property phi to a proof of phi of x. And this can be, there is the simplification rule for that. This is a traditional rule of substitution in predicate, substitution of equals for equals in predicate logic. So let me just show you some small proofs. So, I'm really sorry to be so pathetic after Adam. Yeah?
You postulated it somewhere.
Yeah?
So basically, put it in a global namespace.
Yes?
So do you need to do that, or can you have it also as an implicit parameter of the type?
Yeah, you could have it as an implicit parameter, right? But what you define then, is more like typed predicate logic, because you would have it for one. I presume that's what you're suggesting. You define it once for each quantifier. Is what you are suggesting to put it as a, here, for example, we put a d as a parameter there, which would be implicit in the constructor. Then you can vary. It's of course constant over that definition, but when you use the universal or the quantifier, then you can put different d's in different places, right? So here at least in this file, we have one D once and for all, which is used in the definitions. Yeah, but that's also a good question, of course. Right, let's look at some pathetic proofs. And I think the main thing I want to show here is, you saw Adam displaying proofs using the LTAC language. So LTAC is somehow a special purpose language for what we could say generate proofs, right? I mean, those proofs that generates are actual lambda terms in the type theory of Koch, right, in Galena. But it's not displayed like that. But in Agda, it's displayed like that. Let's see now, it's small proofs. There I have it. Yeah, so we have some proofs about natural numbers. Well, associativity, as you say. So actually, I import. Yeah, so here you see some examples of importing files. So you import files and you open them in order to make the declarations available. In opening them, you can rename some things, like, for example, I haven't shown you mltt.mltt. I will do that on Monday. This is the file for the whole of Martin Löw type theory as defined by Martin Löw. And then, just for no particular reasons, I need to hide plus, because plus in that file means disjoint union and not addition. And I have to hide n because it means, some small natural number types, and I use n for something else here. And for no reason particular, I need to rename R, because I've been so faithful to Martin Löw that I've actually used the same identifiers as him. So I rename that to Refel to make it a little bit more readable. So here you see the proof of, very simple proof of preservation of equality. Yeah, so I should also say that here I use, this is a little, I should have used a different notation, I should have used the other file. But anyway, this means that little a and little a prime are equal in big A. So little a equals a prime, and this is f of a equals f of a prime. And the way we prove that, so we do, this proof that any function f preserves equality, it will be done by pattern matching on, on the proof that two elements a and a prime are equal. So we put the p, that proof, that p belongs to little a equals little a prime in big A, and we do pattern match on that. And you see that there is only one case, and that's reflexivity. And if a and a prime are equal by reflexivity, then they actually will be the same normal form. They will have the same normal form. So in that case, f of a and f of a prime will also have the same normal form. And hence, we can prove that by reflexivity. Yeah, so here you see this explicit way of writing a proof function, Kong, for this little theorem. And here you see, associativity of plus in another notation than Adam's. So here it's written directly in the somehow functional programming language with pattern matching. But of course it uses the same technique, at least morally, because, well, I defined addition with induction on the second argument. So here we do induction on the p rather than on the first argument. But otherwise, what's going on here is analogous to what's going on in Adam's proof. And of course, this way of writing explicit proof terms, it works up to a point, but it doesn't really, people haven't Well, so let's see. So what are the biggest proof people have done? People can do moderately big proof, but I don't think it would do for doing proof of the four-color theorem or anything like that, right? But of course, it emphasizes the fact that proofs are nothing but functions.
Why is it the last one?
Sorry? It's just that when I define plus, I did it by induction or recursion on the second argument of plus. That's the only reason. Adam did it in the other way, or the Coq system did it in the other way.
I have a question on syntax. When you write MNP together like that, are they curried when you actually call associativity?
Yeah, they are. It's a shorthand for the curried version, yes.
Okay. Would you have to write it like that if you wanted to refer to MNP in a type signature? Or is there a way to write it with the arrows that makes it look more curried?
So of course you can write m:\nat arrow.
Oh, you can.
Yeah, and you can also, so another of these million shorthands that you have in Agda is that you can omit the arrow. So you can write just two parentheses after each other. Right, so here we see also, the induction axiom as written in Agda. So, Adam showed what it was like in Coq, and here we see the corresponding thing in Agda. So you see that in order to prove some property, big C of n, for a natural number n, we prove it for the base case, C of 0, and we prove it for the step case, C of suc n, provided we have proved it for n for some natural number n. And this induction, proof of induction is defined by, well, recursion on the major argument, the natural numbers, reduces to the base case or the step case in the two different cases. So you see that, Agda and Coq just differ a bit in syntax. Agda is sort of purposely like Haskell. I should perhaps also mention that there is yet another language which some of you may have heard about called Idris, which is much newer than Agda, which tries to go even one step further to being close to Haskell and a real alternative to Haskell, and by Edwin Brady in St. Andrews. And he is an expert on compilation of dependently typed programs. He has a good compiler for this language. So for those of you who are interested in that sort of direction, this is something, I would recommend you to have a look at. It's otherwise quite similar to Agda. It's probably the language closest to Agda. Yeah, and again, you can prove associativity by pattern matching, but you can also do it directly using the combinator for induction on natural numbers. And then it looks like this. It's just one line where you here encode, here you encode the fact that, let's see, so we should, if you saw, the base case was proved by reflexivity, and here you see that reflexivity is up there. And the step case was proved by appeal to this successor function preserving equality. And here you see an example where Agda required us actually to put in the property that we want to prove as an argument of the induction principle, although I made that argument implicit in the definition. Agda couldn't type check without me putting it in, so I had to, unfortunately. But yeah, so Agda is a little bit demanding sometimes in this way. By the way, I should tell you why. Does anyone know why Agda is called Agda? It's somehow very difficult to know if you're not Swedish. Yes. Yes, it's a hen. It's also hen, So it's, of course, again, the joke is on Coq. Yeah, by the way, Adam didn't tell you why Coq is called Coq. Coq is a triple joke. Coq for coquin. 3 first letters of coquin. 4 is a symbol of France, right? and it's for calculus of constructions. So it's a triple joke, triple pun. Anyway, the first version of Agda was written by Thierry's wife, Catherine, and then someone said, well, you know, if it should be called hen, and then someone suggested, well, the hen Agda, because the Agda is a famous hen in a Swedish song. It's a kind of humorous song, so that's why it's called Agda. It seems like everyone calls it Agda, you know, without thinking that it has got this story. You know, it's a very strange word for an English person, I think, and for anyone else except Swedes and other countries where Agda exists. Does anyone know anyone called Agda? Not a single person. We don't have any Swedes here. It's very common for Swedish people born in the 1890s.
If I remember correctly, Ivar Jakobsen told me his grandmother was named Agda.
You see? Just confirms. Okay, so these are a little, you know, few pathetic, but anyway, proofs in Agda. Maybe I'll just show you before we close for today some small proofs of Booleans too. Let's see what I want. Yeah, Kong is, you know, it's the proof that functions preserve equality. It's just a name I used for that lemma. Boole proofs. Let's see what we have there. Yeah, I think. Yeah, so I don't know what am I. I'm here maybe emphasizing the fact that, I mean, if you say you want to prove the law of double negation for Booleans, that B is equal to not B. Well, what's happening in the type checking there is, you know, that, well, so we prove it by case analysis on the B. And if we put in B as true, then not B can simplify to true. And hence we can apply reflexivity. So this is what's happening all the time during type checking, that the types are getting simplified. And then, you know, the proofs are checked. So I think I know actually the answer. You know, you were questioning whether the dependently typed lambda calculus with a la Curry lambda abstraction is decidable. And I think it's decidable if we know that the type is already in normal form. Otherwise not, but if it is, I think it is decidable.
But isn't system F a subset of that language, and type inference is undecidable for system F?
No, so system F is not a sub-language of this, right? Because system F has the impredicative, you know, the third rule of so that's not a counterexample. Yeah. So I don't have a reference, but I'm pretty sure it's the case. It's somehow what Agda is built on, right? Yeah. Okay. Yeah, it's maybe more or less the same, but you know, if we want to prove the proposition that B is equivalent to not B, yeah, then we do a very similar case analysis. But it's just that here we are doing it. We're defining equivalence by pattern matching on the two arguments, and for the case that it's true, you know, then the so will turn it into a one-element type, and then we prove the cases with a only constructor for the singleton type. So, in the hands-on session, you know, you will go to my web page and you will look at the exercises there, and you will try to prove them. I mean, there are some which I'll ask you to do some very simple proofs. The first ones really only exercise you to do some little programming in Agda, and then there will be a little bit of proving. Yeah. So yes, I think maybe this is a good point to stop. And I will save until next time. I was going to show you some other uses of the logical framework for encoding other logics, but I think that will be more appropriate to save that for next time. So I don't know where the hands-on session is. That here too? Yes.
Oh, I was just going to point out the exercises seem to rely on some of these files.
So I have already put up the logical framework directory with those files defined in the pure logical framework, and then I can put the files I've shown here too. You know, I can on that web page. Yeah.
Can you maybe make an archive out of it so that we can download one thing and download something?
Yes, I guess so. Yes, yes. So I was going to, show them somehow, give them little by little, and yeah, gradually. If I may change some things too. Okay, more questions? Yeah.
I can point out that you can actually get to that stuff already by just going to the pointer that you gave.
Okay. Yeah. Yes. Yeah. Good. Yeah. More questions or? Yeah. No, there isn't. No. There could, of course, be for some subset of Agda. Agda is a little bit more general in certain dimensions, which may make such a translation quite non-trivial. I mean, it may be of historical interest that, both Koch and Agda's predecessor, Alf, were designed about 1990. Koch had some precursors as well during, the real first stuff on the calculus of constructions. But Agda and Koch were both, as we know them, or Agda's predecessor, in about 1990, in a European project called, it was at the time called Logical Frameworks, actually. And there was a big discussion whether we should design a common core language so that the Gothenburg, the Paris, the Edinburgh languages would all, at least have a common core subset. And of course, was a wild discussion about this, and some people had extremely bad experiences of languages designed by a committee, whereas others were thinking that this would be very good for exchanging proofs and for encouraging European collaboration and so on. But it didn't happen. And so the languages, although there are several proof assistants, very similar in spirit, so that it should actually be possible to have a common core language. It didn't happen, and there has not been much work in that direction.
The other way around, from Koch to Agda, if you don't erase proofs?
No, so I don't think there has been that either. No. Agda is, this version of Agda, which is really Agda 2, which is a complete rewrite of Agda 1. Agda 1 came from about 1997, 98, and this enterprise started about 10 years ago. And of course, Koch has 25 years of legacy. Agda has 10 years of legacy, and there is a big difference. And not many tools have been explored. It's it's very versatile in some respects, but of course there is immense amount of work that could be done in order to make it more of a competitor to Koch. Yeah.
Is there any reason in principle that you couldn't have that translation from Koch proof to Agda proof? There are reasons like the use of axiom K and induction recursion that you couldn't go the other way, but is there any reason you couldn't?
Well, in Koch, I actually don't know what is the situation with the last version of Koch, but Coq is based on the calculus of inductive constructions, which is impredicative, which has that rule which lets you go, you know, from, lets you construct a small type by quantification over, you know, all small types. This you don't have in Agda, so that's somehow a principal reason why you couldn't do it if you wanted to do that aspect of Coq.
It has that in prop and set, but it doesn't actually have that in type.
Right. So yes, yeah. It might be possible to do some translation for that fragment. Sorry.
It's no longer true in set by default.
No.
Coq's set is no longer predicative by default.
Right. Right. Yeah. Yeah.
If I remember correctly, there was a framework initiative and a common algebraic specification language.
Oh yeah.
But I don't think there are any translations in or out.
I mean, such things are a bit difficult. I remember we had, Agda was actually started as a joint project between a Japanese group in the AIST Institute, Advanced Institute of Science and Technology in Japan, and Chalmers. And because they really wanted to use Agda for really practical stuff, as much as practical as they could. And when we at some stage started changing the syntax, people there started taking the trouble of, writing an automatic translator from the old library to the new library, a very boring thing, which only survived a few years because then there was a complete redesign of the Agda system. So all that effort was somehow wasted. And I think this is somehow the problem. Before languages really stabilize very much, such translations are probably of doubtful value. I mean, Coq is of course very, it's a language which people really use. Agda is more of an experimental language still, I would say. It's used quite, very many papers have been written using Agda for writing bits and pieces, but not such big things. It's after all only for presentation at conferences and so on. Okay, so yeah, you know better than I where the hands-on sessions are. Is it here? Yeah, okay, good.